Hello, fellow students. Today we are going to continue with the adjacency matrix. We are going to do a new exercise related to this topic. So stick around and enjoy yourselves. Okay, so let's start the exercise. Considering this graph, and remember that a graph is determined by this set where we have 7 nodes, we have 11 links, and we have an application P. And then this application says which nodes are related to each other with the link, right? So for instance, if we the application of E1 means that it is linking the nodes 1 and 2, right? If we apply E2, it means that it is linking the nodes 3 and 2. So the first thing that we are going to do is to draw this graph before working on the adjacency matrix. They are asking also by the directed version of the graph, right? So we are going to start by the directed version, and we are going to start by drawing the 7 nodes. One, 2, 3, 4, 5, 6, and 7. Okay, so as you see, this first set tells that we have 7 nodes, so we draw 7 nodes. And now we are going to draw the 11 links. So the first link, E1, links the nodes 1 and 2. So we draw a link between 1 and 2, right? And this is E1. E2 links 3 and 2, so 3 and 2, and this is E2. E3 links 1 and 3. So we draw the link, and okay, this was the directed version. So remember that in this case, we need to put an arrow at the end of the line, right? So for instance, in E2, it links 3 and 2, so the final node is 2. In E3, it links 1 and 3, so the final node is 3. For E4, it links 1 and 6, so the final node is 6, and this is E4. Right, then we have E5, which links 6 and 3. So we put the arrow on the 3, and this is E5. Then E6 links 3 and 4. E7 links 6 and 5. E8 links 4 and 5. E9, 5, and 6. So as we already have one link from 6 to 5, but now we are going to have another one from 5 to 6, right? Which is E9. E10 links 7 and 7, so that means that we have a loop here. E11 links 1 and 1. Right, so this is the graph. We can make also the non-directed version, which is pretty straightforward. We only have to draw the nodes in the same position. And now we draw a link, a non-directed link for each directed link that we have on the left, right? So for instance, for E1, we have non-directed link, for E2, for E3, E4, E5, E6, E7, E8, E9, E10, and E11, right? So this is D, and this is the non-directed version of this graph. The only thing that you have to take into account is that you could think that here we could simplify these two links into one, right? When we make the non-directed version of the graph, but you can't do that because these are two different applications, right? Two different relations. So that means that you have to represent these as two different links. If we do the transition, the opposite transition from non-directed to directed, you see how the transformation is different, because for each of these links, we would need two directed links, right? Except on the loops. So that's a bit different. Okay, so now we have to do the adjacency matrix of these graphs. We start by the first node, E1, which is linked to E1. It is linked to E2, to E3, not to E4, not to E5, to E6, right? And not to E7. So we have, remember that we count the number of direct links that we have from one node to the other, right? And the node where we start is represented by the row of the matrix. So as we are in the first row, we count the links from the first node to other nodes. On the second row, we count the links from the second node to other nodes, right? So from 2 to 1, we don't have any direct link. From 2 to 3, we don't have. From 2 to 4, we don't have. To 5, to 6, to 2, to 3, to 4, to 5, to 6, and to 7, right? Because there is no link, there isn't any link coming out of 2, right? So we have all zeros in this row of the matrix. We pass to the third row, and from 3 we don't have any link to 1. We have 1 link to 2. We have no links to 3, 1 link to 4, no links to 5, no links to 6, and no links to 7. We pass to the fourth node, and we only have 1 link to 5, right, on the fourth node. So we don't have to 1, to 2, to 3, to 4, but we have 1 to 5, 0 to 6, and 0 to 7. Right, as you can see, on the fourth node, we only have 1 exit link that goes to 5, right? That is why in the fourth row and in the fifth column, we put a 1. We go to the fifth node, and we don't have any link to 1, to 2, to 3, to 4, to 5. We have 1 to 6, and 0 to 7. We pass to 6, to the sixth row, and we don't have link to 1, to 2, to 3. We have 1, to 4 we don't have, to 5 we have 1, to 6 we don't have, and to 7 we don't have. And then 7 only has a link to itself. So we put a 1 in the last column and the last row. Right, so this is the adjacency matrix of the directed graph. And now we are going to do the adjacency matrix of the non-directed graph, right? So the process is the same. We need to count the number of links coming out of each node, right? We start with the first node. We have a link from 1 to 1, from 1 to 2, from 1 to 3, to 4 and 5 we don't have, to 6 we have, and to 7 we don't have. We pass to the second node, and on the second node we only have a link to 1 and to 3. Right, so we put the ones on 1 and 3, the first and the third position, and that's all. We pass to the third row, and on the third node we have links with 1, with 2, with 3, with itself we don't have any link. We have a link with 4, with 5 we don't have, with 6 we have 1, and with 7 we don't have. We pass to the fourth node, and we don't have a link with 1, we don't have with 2, with 3 we have a link, with 4 we don't have, with 5 we have a link, with 6 we don't have, and with 7 we don't have. We pass to the fifth node, and we don't have link with 1, we don't have link with 2, we don't have link with 3, with 4 we have a link, with 5 we don't have, with 6. In fact, we have 2 links with 6, right? So we put 2 here, right? If you see, you realize here we have 2 links from 5 to 6, right? So in the fifth row and the sixth column, we put a 2, right? And from 5 to 7, we don't have. On 6, we have link with 1, link with 3, 2 links to 5, 0 links to 6, and 0 links to 7. And on 7, again, we only have a link to itself. So this is the adjacency matrix of the non-directed version of this graph. Okay, this doesn't look very good. Just let me fix it a bit. G of D. Okay, so what's the difference between these two matrices? As you can see, we have more ones on the matrix on the right, because now the links are bidirectional, right? So that means that this link, for instance, doesn't join only one, doesn't go only from 1 to 6, but also from 6 to 1. So we will have more ones on this matrix. And we can have also 2 or more, right? Depending on the number of links that we have between 2 nodes. Well, there is another difference, but we will see it later. So let's go to the next question. And the next question is, just let me 1 second, let me copy the question here. So it says, looking at the second row of the adjacency matrix of the directed graph, can we say that 2 is an isolated node? Okay, so first let's mark the second row, right? The second row is this one, and they are asking if this node, if 2 is an isolated node, right? So the first thing is we should go to the theory and read what is an isolated node. Right? An isolated node is it is not linked to any other node, right? Even itself. Right, so it's a node that is not linked to any other node, even itself. It's not even linked to itself. Can we say that about the node number 2? No. Looking into this row, we can only say that there isn't any link, any edge coming out of the node number 2, right? There isn't anything coming out of this node. But we should also check the second column, and we can see how we have 2 links that are where 2 is the end point of these links, right? So it means that it's not isolated. So let's write the answer here. No. The only thing we can say is that there is no link coming out from the node 2. But 2 could be the end point of some link. To check it out, we only need to see the second column of the matrix. Okay, let's do the next question. Okay, now they ask what information is given by the row and column 7 of both matrices. So let's mark the row and column 7, right? It is 2, 3, 4, 5, 6, 7. This is the 7th row. And this is the 7th column. And this is the 7th row. And this is the 7th column, right? So the information that is giving is that on the 7th node, we have a 1 on the, let's say, diagonal, right? On the position 7, 7 of both matrices. That means that the only link that is coming out of 7 is a loop, right? Because it's a link that is coming out of 7, but also the 7 is the endpoint, right, of that link. So in this case, is giving this information, right, that there is a loop on the node 7. So let's write it here. The 7th row points out that there is only one link coming out of the node 7, where 7 is also the endpoint of that link. Right. 7th column tells that there is only one link pointing towards the node 7. So in conclusion, there is a loop in the node 7, right? Okay, and let's do the last sub-question. I'm going to do it here. Don't have much space left. So okay, the last question is what can we say about the summation of all the elements in the adjacency matrix of the directed version of this graph? No, okay, yeah. They are asking about the summation of all the elements in the in the directed version. Okay, that's right. Well, it's easy. If we add all the elements here in this matrix, we should have the number of the number of links, right? The total number of links that we have on this matrix. Right, so that means that we should have 11 ones, right, on this matrix, right? So if we add all the elements, right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So that's correct. So let's write it down. The summation of all elements in the matrix corresponds to the total number of links or edges in the graph. Right, but remember that this is because this is a directed graph, right? If the graph is non-directed, the answer could be different, right? So this is only in case that we have a directed graph. Okay, so that's all for today. We will continue with these basic concepts on the following videos. I hope you enjoyed. If you have any question, please let me know in the comments. So ciao, ciao, and see you again.